So today we're going to talk about how symmetry and group theory can help us with NMR spectroscopy. And this is a much lighter subject than when we were looking at our infrared spectroscopy. It's going to be much simpler for everyone to understand. So previously you probably talked about NMR spectroscopy in terms of chemical environments. So now we're going to talk about it in terms of symmetry, and it's going to end up being that any atom that is symmetry equivalent to another atom is also physically and chemically equivalent to that other atom. So I've highlighted here the bromine throughout in yellow, the chlorine here in this sort of teal color. And so this is how most likely I would give you the structure in a very unsymmetric looking orientation. And so one of the first things that you might do with this is to orient it in a way that looks more symmetric. So when I put both of the atoms here, one up and one down, the molecule we'll see real soon is going to have mirror planes and C2s. So I put my two non-hydrogen atoms up and down. And then the only thing that this structure really is useful for is for us to go ahead and put in our explicit hydrogens. So these skeletal type structures, we leave off hydrogens because there's hydrogens everywhere, but we just want to check that we put in all the hydrogens that we need. So this carbon, for example, has 1, 2, 3 bonds to it, so it has to have 4 bonds. Carbon always is craving 4 bonds, and so that fourth bond is a hydrogen that we've left out of the structure. Well, even once we've done this, it's looking less symmetric than it is because you'll remember that this is one of two possible resonance structures. The real structure of the molecule is better represented as either this structure here or this one here, where the bonding, the pi bonding is delocalized. So once we have either one of these type of structures, we can go seeing about that we have a few symmetry elements in this. So once I've drawn it this way, I have a C2 axis that goes through here. Okay, that C2 flips the molecule over. It goes through chlorine, carbon, carbon, and bromine. Along that axis, I have two different mirror planes. One that is the plane of the molecule, the other one which is perpendicular to that. And of course, the last symmetry element is always identity. So what's the reason for doing all this? I can go through now and just drop a label somewhere and then see where the symmetry operations will carry that label. So I'm just picking a random atom here. If I was doing proton NMR, say I pick this hydrogen atom right here, and then I see where it can get carried in the molecule and where it can't. So this hydrogen A, if I do either a C2 rotation or a mirror, gets carried over here. Okay, and so I do that until I can't move it anywhere else. And I've hit that wall. I can't move it anywhere else. Because none of the symmetry operations will carry A down here to the bottom. So once I've hit a wall, I can pick any atom that's unlabeled. I call that one B, and then the same process will carry B over here. Either a C2 or a mirror plane will carry B over here. And so I have two unique hydrogen atoms in that atom, in that molecule. This one, I could go through also. I'm going to do it here with a different color. I could ask you about C13. Remember, each one of these little dots here is a carbon atom. So I could also ask you about C13. So now I'm talking about the carbon that's right there. So that one's A. C2 rotation would carry A over there. Okay, this first part's going to look really similar. B carries into B. But no symmetry operation of this group will carry those labels to this point or that point. So I'm going to go ahead and label this one C. Okay, and then I'm stuck again. No operation, no symmetry operation will carry it down here to point D. And so I have 4 unique types of carbons in that molecule. And you can go back and be a good organic chemist and think about these. So A here is a carbon that is attached to a carbon that's attached to chlorine. This carbon is a carbon that's attached to a carbon that's attached to chlorine. This carbon is attached directly to chlorine. This carbon is attached directly to bromine. So all of your organic knowledge also works. This is very complementary to what we're talking about here. So let's look at a couple of few more complicated molecules that we have here. We can go through and kind of follow this same process. So hydrogen, 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 hydrogen. Okay, so this molecule, there's my hydrogens. Okay, just making sure that all those carbons have 4 bonds. And the reason it's good to think about these hydrogens right away is, well, check out this carbon right here. It's only got 2 bonds to it. And I know any missing valence to get me up to 4 are hydrogen atoms. And so, and this guy's going to be tetrahedral, so let's make one of those come out of the plane and one of those go into the plane. Well, then this doesn't have a whole lot of symmetry to it. It's a planar molecule, except for those 2 hydrogens. This only has a mirror plane. It doesn't have any other symmetry operations. So this has got a mirror plane. The mirror plane is the plane of the carbons. So let's go through and do some assignments and see what we can get for this one. Put an A up there, picked any random spot. No symmetry operation will carry this A, say, down to here, because it would take this CH2 group and move it down. So I can't do that. So I'm already stuck, and each one of these is going to happen. B, C, D. No symmetry operation will move those anywhere else. E, F. Well, I got one and only one symmetry operation in this, a mirror. Well, that mirror will do one thing. G, which is coming out, and G, which is going back. Okay, those two will be symmetry equivalent to each other. So those would give us the same resonance in the proton NMR. All right, here's a more complicated version of what we saw earlier. So let's go through, and it's oriented pretty well. All of those is conjugated, so I'm not going to worry about exactly where those double bonds are, except to go through and see where to put my hydrogens. So 1, 2, 3, I need a hydrogen here, hydrogen here, need a hydrogen here. 1, 2, 3, need a hydrogen here. Oh, I do not need a hydrogen right there where the rings join because I have 1, 2, 3, 4 bonds there already. Okay, and then if I go through this molecule, I'm going to do the same sort of thing. I'm going to go and just label any random hydrogen. So I'll label this hydrogen up here at the top. This is a pretty symmetric molecule. It's got a bunch of C2 axes all over the place. So there's a C2 that would go that way. I could do a C2 that goes through here, and there's also a C2 that's right there in the middle. So pretty symmetric molecule. This is actually the D2H point group, so it's highly symmetric. So A gets carried over here by a C2. This long ways C2 will carry those A's down here to the bottom, but nothing that I can do to this molecule will move the C2s to, will move those labels to these positions. So I need to go and label something B. So B, my C2 will carry the B over here. The other C2 will carry the B's down to the bottom. But nothing will carry it to these positions. So finally, C and C. Okay, so there's 3 unique types of hydrogens that's in there.